Let's take a look at entropy in the second law of thermodynamics. So the first law of thermodynamics, remember, is that Q equals delta U plus W. The thermal energy that's exchanged is equal to the change in the internal energy of a system plus the work that's done. And yeah, we have to worry about whether the thermal energy goes in or out of the system, whether the work is done on the system or the environment, all that stuff. But really, at its heart, the first law is a statement of energy conservation. The second law of thermodynamics can be expressed in many different ways, and each of those ways of expressing it emphasize slightly different ideas. So I'm going to give three different versions of the second law. The first is the Clasius version, and it says, energy will only transfer from cold to hot if work is done. This cannot happen spontaneously. So that kind of makes sense, right? Thermal energy won't just go from a cold reservoir to a warm reservoir unless you do some work to make that happen. Okay. The Kelvin version is that thermal energy cannot be converted to work with 100% efficiency. Okay, so that seems important. You cannot take thermal energy and completely convert it to work with 100% efficiency. You're not allowed to do that. Okay. The third version is called the entropy version, and it says the entropy of an isolated system, including the universe, will always increase. Okay, so seems fine, except what the heck is entropy? Well, let's define entropy. Entropy is a measure of the disorder of a system. And if you're like me, when you see that, you don't like it. Because I remember when I saw this and I said, well, what the heck do they mean by disorder? That doesn't seem like a very physicsy term. Disorder does not seem like a quantitative idea. So we're going to have to define that a little bit better, and we'll do that in a moment. But before we do that, I want to go back to this entropy statement of the second law and say it with this term disordered, because we can rewrite it as an isolated system will always become more disordered. All right, well, what the heck does this disorder mean? I mean, if you leave a house of cards on the table, sure, eventually it'll fall down, and that seems like then it would become more disordered. Sure. But what if we wait 1,000 years, or 1,000,000 years, or 1,000,000,000 years, and these cards, they decompose into a bunch of uniform dust? Is that more disordered then, or is it less disordered if we just have a table full of dust? I'm not sure. So what we have to do is we have to go to this idea called microstates. And microstates are the possible arrangements of the parts of a system. So let's do an example. Let's say our system consists of 4 coins. The 4 coins can either be heads or tails. So what I'm going to do is I'm going to make a table of the states over here, and then all the possible microstates for each state. So for example, one possible state would be for 4 heads. Another possible state would be 3 heads, 1 tail. Another possible state, 2 heads, 2 tails. Or 1 heads, 3 tails, or 4 tails. The microstates are all the possible ways that the coins can be arranged to form that state. So for the 4 heads state, there's only one possible microstate, and that's heads, 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 heads. For 3 heads, 1 tail, there are 4 possible microstates. Heads, 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 tails, heads, heads, tails, heads, heads, tails, heads, heads, tails, heads, heads, heads. For 2 heads, 2 tails, there's 6 possible microstates. Heads, heads, tails, 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 heads, heads, tails, heads, tails, heads, heads, tails, tails, heads, heads, tails, heads, tails, tails, heads, heads, tails. For 1 heads, 3 tails, it's kind of the flip version of 3 heads, 1 tail. There's 4 different possible microstates. So there's heads, tails, 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 heads, tails, 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 heads, tails, 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 heads. And for 4 tails, there's only one possible microstate. Tails, 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 tails. All right. So if we're looking at this, the most likely state is the state with 2 heads and 2 tails, right? 37.5 of all of the microstates are in that state. The least likely state is either 4 heads or 4 tails. They're equally unlikely. There's only about 6% of the states that are either 4 heads or 4 tails. Now, let's say we had a similar system, but it's made out of 100 coins. Well, we're not going to do that. We're not going to write it out right now, but believe me when I say, there's about 10 to the 30 possible microstates. And the most likely state for that system is half heads and half tails. Turns out there's about 10 to the 29 states that are half heads, half tails, or 10% of all the possible microstates are that state. The least likely would be to have 100 coins all heads, or 100 coins all tails. Each of those, the probability is only about 10 to the minus 30. So, back to the idea of what disordered means. More disordered means that there's more possible microstates that look that way. That means that the microstate is likely. It's not special. So in our 4 coins example, the more disordered state is the one with more possible microstates. So that's the 2 heads, 2 tails. That's the more disordered state. A less disordered state means that there are fewer microstates that look that way. It's more special. It's less likely. So the least disordered microstates in our 4-coin system would be 4 heads or 4 tails. And in our 100 coins system, the most disordered system would be the one that has half heads, half tails. And the least disordered system would be the ones that has all heads or all tails. Okay. So for a simple system, this might make sense, or we might be able to make sense out of it. However, now try to apply the idea to, say, a canister of 1 mole of ideal gas. Then it becomes tricky, because now we have to imagine all the possible microstates of 6.02 times 10 to the 23 molecules. Well, there's going to be a whole heck of a lot of microstates, of ways that you can arrange 6.02 times 10 to the 23 molecules that are in a container. So we're going to introduce another idea called multiplicity. It's represented with the Greek letter capital omega. And the multiplicity is the number of ways that a certain system can be arranged without altering its macroscopic properties. And when I say macroscopic properties, if we're talking about an ideal gas, for example, that would be, say, pressure and temperature. So we can define the entropy in terms of the multiplicity. The entropy of a system is equal to Boltzmann's constant times the natural log of the multiplicity. So the power of this is it relates entropy, which is a large-scale macroscopic property of something, of a system, to the microscopic properties of the system, because that's what the multiplicity is. Now, this equation is not something that we would realistically be able to calculate for gases. If I have 6.02 times 10 to the 23 molecules in a container, I'm not going to be able to calculate the multiplicity very easily. At least in most cases I won't be able to. And so I won't be able to calculate the entropy in this case. But it does tell us that if the multiplicity is larger, then the entropy is larger. And if we go back to our statement of entropy in the second law, it says the entropy of an isolated system always increases. Well, if the entropy of an isolated system always increases, that means that a system will always move towards a state where it has a greater multiplicity, where there are more ways to arrange the system without altering its macroscopic properties. All right. Now I'm going to write down a different equation involving entropy, and that is this. The change in the entropy of a system is equal to delta Q over T. Now, delta S here is the increase in the entropy of a system, and delta Q here is the thermal energy that's transferred into the system, and T is the temperature of the system when the thermal energy is transferred into it. And this equation only works if the temperature is constant. Now, the power of this equation is that it relates entropy to macroscopic properties, so the thermal energy, the temperature. The last equation we saw, with Boltzmann's constant and the multiplicity, that relates entropy to the microscopic properties. This new one relates entropy to the macroscopic properties. Now, going back to our entropy statement of the second law, we can now interpret it to say that if we have a system that is going to change, it will change in such a way, if it's isolated, in order to increase the entropy of the system. It will become more disordered. It will move to a state which has greater multiplicity. Now, another idea that is not explicitly shown in the second law, but is important to understand, is that if you have a non-isolated system, it turns out that the entropy in a non-isolated system can actually decrease inside of that system. But if that does happen, then the entropy outside of the system must increase. This is particularly important in biological systems. So, for example, let's say that you have a baby, and that baby is the system that we're looking at. Well, as a baby grows up, the baby increases in mass, and actually the entropy of that system decreases, because you get more and more mass being added in a more ordered way. Well, how can that be? If the entropy of a system is supposed to increase, how can we have, babies growing into children, growing into adults? Well, the way is that biological systems, such as a human or a baby, they're not isolated. If it's not an isolated system, then the disorder, the entropy, does not have to increase. It can decrease. Now, that comes at the cost that outside of the system, the entropy does have to increase. So, for example, as a baby grows up into a child and then to an adult, yeah, the entropy of that system is decreasing, but outside of the baby, the entropy is increasing.